Hi Hooks. Now that we know something about solutions, we can talk about some of the most widely used solutions in chemistry, and those are acids and bases. So this is just a summary table of some of the things, common properties of acids and bases. Acids and bases are both electrolytes. They both separate into ions in solution. You should not taste any acids in lab. However, many of the acidic and basic foodstuffs that you might eat, acids tend to taste sour. Most fruits are acidic, especially citrus fruits, oranges, lemons, limes. Those have a sour taste. Bases have a tendency to taste more bitter. Acids turn litmus indicator red, whereas bases turn litmus blue. That's not the only acid-base indicator, though. Phenolphthalein is a common indicator that we have used in class. In acid, phenolphthalein is colorless. It looks like water, but then in the presence of a base, it turns pink. Acids undergo a variety of characteristic chemical reactions. For instance, they react with metals to form hydrogen gas. Bases tend to feel slippery. If you've ever kind of used bleach with your laundry, then sometimes your fingers feel very slippery after you've handled the clothes, and it just feels like it takes a long time to wash that off. Some examples from your household of acids would be vinegar, milk, soda, apples, citrus fruits, whereas examples of bases would be ammonia, lye, antacid, baking soda. So those are some kind of properties of acids and bases. One way that we categorize acids and bases is using their pH. And so the pH of common substances are listed here. You can see that pH is a scale that goes from approximately 0 to 14. You can actually go lower than 0 or higher than 14, but between 0 and 14 is most common. If you're exactly at 7, you're exactly neutral. And as soon as you're anything below 7, you start to get acidic. If you're just a little bit below 7, you're slightly acidic, but if you're much below 7, then you're strongly acidic. Same thing in the neutral, in the basic range. If you're just slightly above 7, you're just slightly basic. If you're far above 7, then you are strongly basic. And you can see here just battery acid versus black coffee, blood and seawater versus bleach and sodium hydroxide. So we can use the pH scale to measure acids and bases, but how do we identify them? How do we define acids and bases? There are a few different definitions for acids and bases, and the first one we're going to talk about is the Bronsted-Lawry definition. According to Bronsted-Lawry, acids are proton donors. A proton is just a hydrogen ion. And since hydrogen is the first element on the periodic table, it only has one proton, and a hydrogen atom would be surrounded by one electron. But because this is hydrogen with a positive charge, it has lost that one negatively charged electron, and it is just the proton left behind. This is why proton and hydrogen ions mean the same thing. Bases are the opposite of acids, so it's not surprising that bases are proton acceptors. So here in this reaction, we have hydrochloric acid plus water, and you can see that hydrochloric acid is an acid. It donates its proton to the water, so it loses its hydrogen, and water gains that hydrogen. that hydrogen ion. HCl is the acid as the proton donor, and water is the base as the proton acceptor. Arrhenius is another scientist, and he had a different definition of acids and bases. He said that in aqueous solutions, acids form hydronium ions. That's this H3O plus ion that we actually saw on the previous screen, so you can see why acids might form hydronium ions if they're giving up that hydrogen. Acids form hydronium ions. So again, we can see here HCl plus water is making this hydronium ion plus chloride ions. So this is why we say that acids are electrolytes, because they are splitting up into their ions. We've got the chloride ion and the hydrogen ion. Although the hydrogen ion doesn't stay by itself, it attaches to the water. So you can see that HCl is the acid in this example. The Arrhenius definition is really consistent with the Bronsted-Lawry definition. It's just that Arrhenius's definition really only applies to aqueous solutions. In chemistry class, we do almost always do our acid-base reactions in aqueous solution, so this is an appropriate definition, but it is limited to being in solution. So let's look at how we ionize acids. If we start with hydrogen bromide as our acid, and it reacts with water, then we're going to create, because hydrobromic acid is an acid, it is going to create the hydronium ion, and since it creates the hydronium ion by donating its hydrogen to the water, then the bromide ion is going to be left all by itself. Notice a couple things about writing these equations of how acids react with water. Notice that at the start of the reaction, there's a total charge of 0. Therefore, at the end of the reaction, there must be a total charge of 0. Here I've got a +1 charge and a -1 charge, and that adds up to 0. So when you kind of write these ionization, just make sure that your charges at the beginning equal your charges at the end. For nitric acid, HNO3, when that reacts with water, again we form the hydronium ion. And when we give up the hydrogen to water, what's left behind is this nitrate ion, NO3, with a charge of -1. Again, my total charge at the beginning is 0, and my total charge at the end is 0. That's what an acid is, according to Arrhenius. So, what's a base? According to Arrhenius, a base forms hydroxide ions in aqueous solution. So here's an example of ammonia and why ammonia would be classified as a base according to the Arrhenius's definition. And what we see here is that ammonia, NH3, actually steals a hydrogen ion, a proton, from water to become NH4. And when that happens, water isn't water anymore, it's left as a hydroxide ion. So bases form hydroxide ions in solution. Sometimes bases form hydroxide ions because they've stolen a proton from water. Other times it happens because the base itself contains hydroxide ions, and we'll look at an example of that in just a moment. But for now, I want you to see that ammonia, NH3, is a base because it is a proton acceptor. It is accepting a proton from water. So, potassium hydroxide is one of those substances that has hydroxide ions in the formula, so it's fairly obvious where the hydroxide is going to come from here. Potassium hydroxide, when you dissolve it in water, is going to split into potassium ions in solution plus hydroxide ions in solution. So you can see here that this fits the Arrhenius definition of a base. Magnesium hydroxide, solid, when you dissolve it in water, produces magnesium ions in solution, plus hydroxide ions in solution. And just like we did when we were talking about kind of colligative properties and thinking about how many particles a particular substance splits into, we need to take into account that there are 2 hydroxide ions here. So that's why I wrote a 2 in front of the hydroxide symbol. I've been naming these acids and bases for you thus far, but you do need to be able to name and identify different acids. The bases we've actually already learned. The bases don't generally have any different naming system to them. Potassium hydroxide, sodium hydroxide, you name them as normal ionic compounds. But acids, we do change up their names a little bit. Acids, the formula starts with H. H is the first element you see in the formula. If your acid contains just 2 elements, then it is what we call a binary acid. And the naming for that acid starts with a hydro, and the ending is IC. So for instance, HCl is hydrochloric acid. HBr is hydrobromic acid. HI is hydroiodic acid. So you use a hydro prefix, then you say the element, but you change the ending of the element to ic, and then you say the word acid. There's a different category of acids that have 3 elements, and these are oxyacids. And examples of those would be things like HNO3 or H2SO4 or H3PO4. If the ion has an ATE ending, then that ATE becomes IC. So this is a nitrate ion, and it becomes nitric. This is nitric acid. This is a sulfate ion, so it becomes sulfuric acid. This is a phosphate ion, so this becomes phosphoric acid. On the other hand, if we look at like HNO2, this is the nitrite ion, so this becomes nitrous acid. This is the sulfite ion, so it becomes sulfurous acid. Here is the phosphite ion. So this is phosphorus acid. So there is a system for naming the acids based off of whether there are just two elements making up the compound, making up the acid, or if you have an oxyacid where there are three elements making up the acid formula. So just to summarize this in kind of word form instead of a tree form, a binary acid is an acid that contains only two different elements. Hydrogen is always one of the elements. The other element will be a nonmetal. So pause the video and take a moment to try to name these. HF is hydrofluoric acid, HCl is hydrochloric acid, and HBr is hydrobromic acid. Oxyacids, on the other hand, are acids that are composed of hydrogen, oxygen, and a third element, which is usually a nonmetal. Usually, your formula starts with hydrogen, one or more hydrogen atoms, and then it's followed by a polyatomic ion. Based off of the polyatomic ion name, you can then predict the acid name based off of that. So take a moment to pause the video and try to work through these yourself. The acetate ion ends ATE, so the ending becomes ic, acetic acid. The nitrite ion becomes nitrous acid. The acid with the nitrate ion becomes nitric acid. The acid with the phosphite ion becomes phosphorus acid, whereas the phosphate ion becomes phosphoric acid. The acid containing the sulfite ion becomes sulfurous acid, and with the sulfate ion becomes sulfuric acid.